In this exam problem, we have a shopper pushes a 7.5 kilogram shopping cart up a relatively small 13-degree incline, as shown in the figure below. Find the horizontal force F needed to give the cart an acceleration of 1.41 meters per second squared up the incline. Now, for problems like this where I'm dealing with really small numbers, I usually redraw the picture and I really over-exaggerate it to help me visualize the problem a little bit clearly, a little bit more clearly. So on the next page, I've already got the picture started here. So obviously this is way more than 13 degrees, but it's going to help you visualize the problem because it's going to be the same thing, whether this is 13 degrees or 89 degrees, it's going to be the same approach. Okay, so first step is to draw all the forces on the picture that are acting on the shopping cart. And I'm going to assume in this problem that we can ignore friction since we haven't introduced friction yet. So we're ignoring friction. We already have the force of the push acting on the cart, which we're just calling F in this case. But we also know that this cart has a weight that is acting straight down. Now, it's not acting at any angle. Right, you cannot change the direction of gravity, so it's going to be acting straight down to the ground. So I have another force that's going straight down. And we'll say that's the weight from the cart. And we also know that there is a force that is pushing back up against this cart that we call the normal force, and it's just going to be slightly tilted because of that incline, and we'll call that N for the normal force. Now you can see how this almost just looks like a bad or a poorly drawn straight line because that angle is so small. So when I over-exaggerate it, it makes it a lot clearer and makes it seem like some of the example problems that we've seen in the past. So we'll go to the next slide to draw our free body diagram, and which I've replaced the cart with this little gold dot. Now I'm going to draw all of my forces acting from that single point. So I've got the weight acting straight down. So there's my weight force, W. We know we have the force of the push acting perfectly horizontal. So we've got the force of the push acting perfectly horizontal, or you can think about it as being parallel to the ground. So there's F. And we also have the normal force, which is the ground pushing back up against the cart. So that's going to be the normal force, which is a little bit more clear in this picture because we've severely over-exaggerated the 13-degree angle. So we have the normal force acting perpendicular to the ground, and those are all the forces acting in this situation. Now, we want to figure out what the magnitude of the force needs to be horizontally for this cart to be accelerating up the incline, okay, with that acceleration that was given at the beginning, that 1.41 meters per second squared. Okay, now there's our free body diagram. Now the next step is to set up our coordinate system. So as we saw in a previous problem, sometimes it can be very beneficial to tilt our coordinate system. So I'm going to go ahead and do that in this case, even though it may not be as beneficial in this problem. But I want you to get used to, every time you have an inclined plane problem, get used to tilting that coordinate system because you're going to have to do it for most problems that we deal with in this class. So in this case, my coordinate system, okay, is going to be... here's going to be my y-axis, so that's my negative y, and I'm going to define my positive x-axis to be going up the incline. Okay, so up the incline, so that's going to be my positive x, and then down the incline, I'm going to call that my negative x. That's negative x, and then of course, along the normal force, we'll call that positive y. Okay, so there's the coordinate system that we're going to use to solve this problem. Now, like we saw in the previous examples, we haven't proven this, and we probably won't prove it in this class, but just accept it. If you are curious about the proof that this angle is equal to the angle of incline, then just talk to me and I'll show you the proof. So we know that the angle between the negative y-axis and the weight is equal to the angle of the incline. So I'm just going to put here that that angle is equal to 13 degrees. I'll try to squeeze that 13 in there. So 13 degrees. Okay? Now, at this point, you can imagine taking this entire problem and just rotating it to where it looks more like the problems that we've been dealing with all year. So I'm just going to draw that real quick. I'm just going to re-sketch all of this, but I'm just going to rotate it to where the positive y is straight up, negative y is straight down, and so on and so forth. So here it is. So now that's a little bit easier to look at. But there's still one thing that we need to know, because remember, when we're dealing with forces that are not like perfectly along the x-axis or perfectly along the y-axis, we have to break them into their x and y components. And at this point, it looks like we don't know what the angle is for the force that we're pushing the cart. However, if you look at our original picture, we know that the force W is acting straight down. And we also know that the force push is acting perfectly horizontal. Okay, so if that's true, then that means that the angle between those two vectors should be 90 degrees. So there should be a 90-degree angle between those two vectors, which means that if I know that there's 13 degrees between the negative y-axis and W, then to figure out what the angle is from the negative y-axis to F, I just do 90 minus 13 to figure out what that angle is. So 90 minus 13 is 77 degrees, so we'll put 77 degrees right there from the negative y-axis. Okay, that's that angle. And now we're ready to solve. We just have to break all of our forces into their x and y components and then use the component form of Newton's second law to finish solving this problem. So let's start easy. Let's start with the normal force. So the normal force is acting perfectly along the y-axis, so we know that the magnitude of the normal force will be equal to the y component. So the magnitude of the normal force is equal to the normal force in the y direction, which we do not know at the moment. Okay. Now, the weight, on the other hand, we can break that up into its x and y components. Now, remember, we haven't formally covered it yet. That's going to be the next section, but for right now, just remember that weight is equal to the mass times the acceleration due to gravity, so weight is equal to mg. So in this case, if I want to solve for the magnitude of the weight, all I have to do is just say the 7.5 kilogram shopping cart times 9.81, and we know that's going to be acting downward. 9.81 meters per second squared. Okay, now typing that into my calculator, I get approximately 73.575 newtons. And I'm going to keep all those digits. I'm not going to round until the very end. Okay, so that is my the magnitude of my weight. All right, so just for clarity here too, I want to go ahead and write, since we know that the normal force is acting along the y-axis, we know that the x component is going to be equal to 0. So in x is equal to 0. Just want to write that. Now let's break the weight up into its x and y components, and it may be easier if we just go ahead and redraw the triangle for the weight. So we have the triangle for the weight is acting this way, and we have the y-axis side going down, so that's negative y, and we can say that this is the weight, so W, and I'll just draw a dotted line over to the negative y-axis to show you what the triangle we're dealing with. Now, the horizontal side of my triangle is going to be my x component, so that's going to be Wx. And the vertical side of my triangle is going to be Wy. Okay? Now, just using some basic trigonometry and the angle, which we know is 13 degrees, we can solve for both the y component and the x component. So let's start with the sine. So we'll do sine. So sine of that 13 degrees is equal to the opposite, so Wx in this case, so the Wx over the magnitude of the weight, which we solved on the previous slide to be 73.575 newtons. So over 73.575 newtons. 575 newtons. Okay, now just doing some quick algebra here, I find that Wx is equal to approximately 16.55. I'm just going to cut it off there. Okay, but remember, I'm not rounding this. I do not round until the very end. I'm keeping all the digits in my calculator every time that I use this x component. But the way that I got this number is just by multiplying both sides by 73.575. So I get that Wx is equal to 73.575 times sine of 13 degrees. I'm just not going through every single step at this point because I feel like you guys have seen this enough to where we can leave out a few steps. Likewise, for the y component, I'm going to use the cosine. So cosine of 13 degrees. Cosine of 13 degrees is equal to the adjacent, so wy in this case. So the y component over the hypotenuse, which is the magnitude of my weight. So that's going to be 73.575 newtons. And I get that just doing the same thing, doing some algebra, solving for wy, I get that the y component of my weight is approximately 71.68 newtons. Okay, now I'm going to check my signs. I know that the weight is in the third quadrant, which means that I have to go down the negative x-axis and the negative y-axis to get there. So both of these components will be negative. So I just correct for my signs, and now I'm good to go there. So now let's break our f into its x and y components. We'll go ahead and go to the next slide to do that. So I've already drawn my triangle for the force that we're pushing this cart, and you can see that the horizontal component is going to be my x component of the force in this case, and the vertical side of my triangle is going to be the y component. So we've got the f sub y. Okay, now we'll just hit this with some trig and then solve for our x and y components. So we've got the sine of 77 degrees. Sine of 77 degrees is equal to, okay, the opposite, so the opposite side, so f of x in this case. So f of x divided by the magnitude of the hypotenuse. Okay, so we don't know what that is. We do not know what the magnitude of the force is in this case. We don't know what that is, so we just have to leave it as a variable. But I can just rearrange this and solve for f of x, and we find that f of x is equal to the magnitude of the force that we're pushing this shopping cart times sine of 77 degrees. Okay. Now we'll do the same thing for the y component, even though we may not even need it. We may, who knows. So we'll solve using the cosine function. So cosine of 77 degrees is equal to, okay, in this case it's going to be the adjacent side, so fy in this case, so fy divided by the magnitude of the hypotenuse, so the magnitude of the force that we're pushing this shopping cart. So F magnitude. Okay, just hitting this with an algebra stick and rearranging, we solve for Fy, and we find that Fy is equal to the magnitude F times cosine of 77 degrees. Okay, now that we've got our components, I'm just going to check my signs. We know that the force F is in the fourth quadrant, so we have to have a positive x value and a negative y, because we have to go down the positive x-axis and then down the negative y to get to the fourth quadrant. So positive x, that looks good, but my y component needs to have a negative sign out front. Okay, so there we go. Now let's just compile a nice list of all of my x components and all of my y components, and then we'll use the component forms of Newton's second law to finish solving. So here's my list. Okay, now if you think back to the problem, now we want to know what force is needed to give the cart an acceleration of 1.41 meters per second squared. And remember that the acceleration with the coordinate system that we have set up is along the positive x-axis. So in this case, we only need to solve for the using the x components of my forces. We don't even have to worry about the y because the acceleration is in the x direction, which means the magnitude of the acceleration will be equal to its x component. Okay, so in this case, we don't even have to worry about all the y components. We can just ignore those in this case, and we can just work with the x direction. So we know that the sum of all forces in the x direction will be equal to the force that we are pushing in the x direction. So that is the magnitude of the force, times sine of 77 degrees, okay, plus the weight in the x direction, so plus negative 16.55. Now remember, I'm not using just negative 16.55. I'm using all the digits that showed up on my calculator, but it's plus a negative, so it's actually going to be subtracting. So minus 16.55 newtons, and then plus 0 for the normal force in the x direction, plus 0. And all of that is going to be equal to ma. So mass times acceleration. Now the mass of the cart was given at the beginning as 7.5 kilograms. So we just plug that in for the mass. So 7.5 kilograms, and then the acceleration in the x direction is the 1.41 meters per second. See if I can squeeze that in there. Second squared. Okay, almost got it in there. Okay, so we've got the sum of all of my forces is equal to ma. Now we just do some math and solve for the magnitude of the force. So just hold tight. If you feel like fast forwarding through this part, it's just a bunch of algebra, but I'm going to walk through each of the steps. That's that way you can see clearly what I'm doing. Okay, so I'm going to go ahead and say magnitude of the force, okay, times sine of 77 degrees, okay, minus 16.55 newtons plus 0, that's just minus 16.55 newtons is equal to the mass times that acceleration. So typing that into my calculator, I get approximately 10.575 newtons. Now I'm going to add 16.55 newtons to both sides, add 16.55 newtons to the other side, and I find that the magnitude of F times sine of 77 degrees is equal to approximately 27.125 newtons. Now, if you got something slightly different, it's probably because you used the rounded version of 16.55. But remember, I'm not using 16.55. I'm using the 16.5500989702 that showed up on my calculator, and adding that to the 10.575 gives me the 27.125, which also has more digits that I'll carry out throughout my calculations. But it's just too tedious to write here. Now the final step is solve for the magnitude of the force that we're pushing this cart. We just divide both sides by sine of 77. So divide left side by sine of 77 degrees, and then divide the right-hand side by the sine of 77 degrees. And we find that the magnitude in the end, the magnitude of the force that we need to push this is equal to approximately 28 newtons, and that's already rounded to the correct number of significant figures, so around 28 newtons. Okay, and that's the end of this problem. If you have any questions, just raise your hand and ask. I hope you enjoyed this problem.